everyone to our online NPTEL course Environmental Chemistry and Microbiology. I am Professor Anjali Pal from Civil Engineering Department, IIT Kharagpur. I will be covering the environmental chemistry part, and this is my 5th lecture on acids, bases and salts. In this lecture, I will cover the determination of acidity and alkalinity, which often we do in our laboratories, and it is very important to know for environmental engineers to know the acidity and alkalinity for a particular sample. I will discuss that in my this lecture. Acidity, we know that acidity may come from different sources, and acidity may be of mainly in environmental purpose, it may be mainly of two types. One is the strong acidity like mineral acidity, and another is the carbon dioxide acidity that is coming from the atmosphere. And from biological oxidation of organic matter, particularly in the polluted water, also we can see that this type of acidity comes. And mineral acidity is nothing but the strong acids coming from the strong acids, that it like HCl, H2SO4, HNO3. It may come from industrial waste due to oxidation of sulfur or sulfides under bacterial action, or it may come from combustion of fossil fuels because of the formation of carbon dioxide. Now, what is the significance of acidity? Acid waters are corrosive, and also in many treatment procedures such as biological treatments, we have to maintain the pH in some range, say for example, pH 6 to 9.5. So, we have to monitor the acidity very often and time to time. So, it is very important to know the acidity. Now, the causes of acidity as is shown here in details. Say for example, there is an organic compound like glucose. When it is oxidized, this is nothing but that BOD reaction. We all know that in presence of bacteria, aerobic bacteria, it produces carbon dioxide, which is one type of acidity. Or in presence of anaerobic bacteria also some type of reaction may occur for organic compounds. Here also we can see that carbon dioxide may be generated. Otherwise, under anaerobic condition with some bacteria, the same molecule can be may be converted to several weak acids, say for example, acetic acid, propionic acid or formic acid. So, these are also weak acids. And some salts, some salts we have already learnt about salts. Some salts, this is a salt ferric chloride, say for example, or aluminum sulphate, upon hydrolysis can produce some acids. This is like weak base, this is also insoluble, and this is HCl, it is completely dissociated. So, it gives acidity. Similarly, here H2SO4 is produced, so it gives acidity. So, acidity may be different types, and we have to know different types, how much is present, different types of acidity, what is present, how much is present, and what is the effect. All those things fall under the environmental chemistry. Okay. Now, determination of acidity, we know that we use usually in the laboratory, which is very simple, and we can do it by titrimetric method, just using some burette pipette and by proper choice of some indicator. Okay. The indicator, that knowledge also you got in the previous lecture, that the choice of indicator is very important. So, here we will see some application how we can choose the indicator. So, for example, you have a sample which you have some which contains some acidity. Okay. So, acidity, but you have to determine how much is the carbon dioxide acidity and how much is the mineral acidity. How will you do it? Okay. First you take some definite volume of sample. Okay. Sample, say for example 100 milliliter of your sample in a conical flask, okay. And in the burette you take some standard alkali solution. Now, first you add a few drops of methyl orange indicator in the conical flask. In the solution that you have taken in the conical flask, you add a few drops of methyl orange. Now, if it is acidic solution, then the methyl orange will give the pinkish red color. I told you that methyl orange gives pinkish red color in acid. So, it will be pinkish red color, and then you start your titration with addition of alkali, standard alkali solution from the burette. Now, at the equivalence point, at the neutralization point, okay, so the color will be changing, the color of the indicator will be changing from pinkish red to yellow when you reach the equilibrium point. And at this point, my question is, at this point what is neutralized? At this point only the mineral acid is neutralized. Only mineral acids are neutralized at this point, because methyl orange changes its color in the range of 3.7 to 4.3. In this range it changes its color. So, in this, at this point, you know, where you get the change of color of the indicator, here only mineral acids are neutralized. Now, you throw the sample and then you take another lot of sample in the conical flask, and then you add, this time you add phenolphthalein indicator. Okay. Now, phenolphthalein indicator, you know that it gives it is colorless in acid and it is pink in alkali. Okay. So, you have added phenolphthalein in the acidic solution. So, you will see it is colorless, and then you start your titration. Okay. Then from the burette you are adding the sodium hydroxide solution, standard sodium hydroxide solution. Now, at the end point it will become pink, because we know phenolphthalein gives pink color in alkali. So, pink color you will get, and then you will reach the you can say that the acidity is neutralized. Now, at this point what is neutralized? The question is that at phenolphthalein end point what is neutralized? At this point both mineral acid as well as carbon dioxide is neutralized. So, phenolphthalein gives you the total acidity. Okay. Phenolphthalein, when you use phenolphthalein indicator, you will get the total acidity. Okay. Everything is neutralized, and when you add methyl orange as the indicator, you will get only mineral acidity. Okay. And then if you subtract the mineral acidity from the total acidity, then you will get the carbon dioxide acidity. It is very simple. So, you see that two most common indicators, phenolphthalein and methyl orange, by using these two indicators you can easily determine the two types of acidity in your water sample, and also you can determine the carbon dioxide acidity. Very simple, but as I told you that methyl orange little typical indicator, you need a few more means trial to understand how the color change is happening and actually what is the neutralization point, and but it is easy, only a few trials are needed. Now, comes the unit, how will you express the acidity? You learned that acidity and basicity, it is related to pH. So, should we express in terms of pH? Should we express in terms of normality or what? Actually, it is universally accepted that acidity we must in environmental point of view, acidity we have to express in terms of milligram per liter of calcium carbonate. Acidity, alkalinity and hardness, these three things we should express in terms of milligram per liter of calcium carbonate. Okay. Now, then how is the calculation? So, acidity, first you have to determine the using the normal formula, simple, most simple formula V1S1 equal to V2S2. Okay. V1S1 equals to V2S2. Here S1 is in normality term. So, first you use that, then once you know the normality, then you have to convert it in terms of milligram per liter of calcium carbonate, and this is very easy to do by using this formula. So, why 50 is coming? Because 50 is the equivalent weight of calcium carbonate. Okay. The molecular weight of calcium carbonate is 100, and the calcium has valency 2, and only one calcium is there, that is why you have to divide the molecular weight by 2. So, it is the equivalent weight of calcium carbonate is 50. And why the 1000 is coming? 1000 is coming because you have to express in terms of milligram, that is why 1000 term is coming. So, it is very simple formula by which N is the normality of NaOH, A is the milliliter of NaOH that you have used during your titration, and this is the milliliter of sample taken. Say for example, you have taken 100 milliliter, or if you have taken 200 milliliter. So, this is the milliliter of sample taken during the titration. So, this is very simple calculation. Now comes the alkalinity. Say similarly alkalinity determination is also very important. Now, what is the sources and nature of alkalinity? Sources, you see here that we know that there are 3 types of alkalinity. What are the 3 types? OH minus ion, which is giving alkalinity, carbonate ion which also can give alkalinity, and bicarbonate ion which also can give alkalinity. Okay. What is the how the bicarbonate is formed? You know that carbonate bearing rocks, when they react with carbon dioxide in presence of water, they can give bicarbonate. We know all those things. When the hardness is formed, bicarbonate is some type of in hardness also, calcium bicarbonate, we know that it is giving hardness. So, we know that how the hardness is also generated anyway. So, here the we are talking about alkalinity. So, there are basically 3 types of alkalinity. So, how the alkalinity is coming? The some salts like phosphate, silicate. Okay, phosphate, say for example, sodium phosphate. If we think about sodium phosphate, it is a salt, but it is a salt of strong base and weak acid. So, sodium phosphate, when it is dissolved, then it is giving alkalinity. Why? Because it is coming from strong base and weak acid. So, it will generate alkalinity. Similarly, silicate, okay, and borate, humic acid, all those salts of all those acids will give alkalinity. Okay. And in polluted or anaerobic water, salts of weak acid such as acetic acid. So, salts of weak acid, acetic acid means sodium acetate, sodium propionate, sodium sulfide, okay. All those things. Sodium sulfide, say for example, H2S is a weak acid and sodium hydroxide is a strong base. So, sodium sulfide will generate alkalinity. Okay. So, these all contribute to alkalinity, and highly alkaline waters are unpalatable, that also we know. Acidity or alkalinity we cannot tolerate, it has some limit, okay, tolerable limit. Now, this titration is even more interesting than the determination of acidity. How it will be determined? Although the indicators are the same, but the titration is very interesting. Okay. So, as I told you, there are 3 types of alkalinity, OH minus and carbonate and bicarbonate. You have to remember one thing here, that OH minus and bicarbonate, these 2 things cannot stay together. These 2 things, OH minus and bicarbonate, these two alkalinity cannot stay together. Why? It is a common sense. Why? Because OH minus immediately will react with bicarbonate to form water and carbonate. So, these 2 things cannot stay together. Now, this thing you have to keep in mind. Now, say for example, I have a sample, water sample, which I want to know what is the alkalinity of this solution. What I will do? So, I will take say 100 milliliter of the sample in the conical flask. Okay. Then first I will add a few drops of phenolphthalein indicator there. When I add a few drops of phenolphthalein indicator, then because it is say for example, it is alkaline, if it is alkaline, then it may give pink color, okay, alkaline. So, it will give pink color because phenolphthalein gives pink color in alkaline water. Okay. Then I will start the titration. I will start the titration by taking the acid in the burette. So, I will add from the burette, I will add the standard acid solution in the conical flask, that is in the solution, in the sample solution. Now, what is the color of the indicator here? Because I have started with alkaline solution, so it may be pink. Okay. If it is pink, then I will start addition of acid. So, at the neutralization point, it will be colorless. It will be colorless because I am titrating with acid. So, neutralization point will be colorless. Okay. Now, what is question is what is neutralized here? Okay. What is neutralized? There are different types of alkalinity. So, what is neutralized here? Here actually OH minus is neutralized and bicarbonate and carbonate is neutralized half. So, it is the half neutralization of carbonate. Okay. So, we have to remember that at this point with phenolphthalein indicator, the whole amount of OH is neutralized and half of carbonate is neutralized. Bicarbonate is not yet neutralized. Okay. Carbonate is neutralized half. Okay. Now, what is the color here? It is colorless, right? It is colorless because we have already reached the equivalence point of phenolphthalein. Okay. So, means using phenolphthalein. So, here it is colorless. So, in this case you do not have to throw the solution, you continue your titration. Only thing you have to note down how much volume of acid you have added. Okay. You note down. Then you add methyl orange indicator here. Okay. You add methyl orange. So, it will show which color because you are determining the alkalinity. So, it will show the color of methyl orange, that alkaline in color, that means it is yellow color. Okay. And then you are adding acid from the burette. So, you continue your titration and then at the neutralization point you will get the color of methyl orange, pinkish red, that is the color in acid. Okay. At this point what is neutralized? At this point actually if there is bicarbonate, that will be neutralized and the remaining half of the carbonate will be neutralized. Okay. So, at the methyl orange indicate that end point you will get the whole amount of bicarbonate and the remaining portion, that half portion of the carbonate you had already remaining, that will be neutralized. Okay. So, by knowing, then you have to know the volume that you have added. So, first time you have added phenolphthalein and you have noted down the volume required of the acid, and second time from there you have continued the reaction titration and then you have noted down the final end point, what is the volume. By knowing these two, you can easily calculate how much is the OH minus, how much is the carbonate and how much is the bicarbonate easily. But one thing you have to remember that OH minus cannot stay together with bicarbonate. If you remember this, then you can easily calculate, by knowing these two titer values, you can easily calculate the different types of alkalinity that is present in your water sample. This is very simple, but very useful, very useful. Now, as I told you that for alkalinity also the unit we should use not the normality, not the pH, but we have to use the milligram per liter of calcium carbonate, same way that we did for acidity. So, calculation is also similar way. So, V1 S1, first you do the V1 S1 equals to V2 S2 and you get the normality. And then to convert the normality you can multiply it with 50 and 50 to get this in terms of calcium carbonate. So, the formula is becoming alkalinity in terms of milligram per liter of calcium carbonate is A is the volume of the acid used, n is the normality of the acid and 50 into 50 into 1000 and by the milliliter of sample taken. This depends on you whether you have taken 100 milliliter sample or 200 milliliter sample or 250 milliliter sample, whatever you have used, you have to according to that you have to calculate. Okay. So, these two titrations are very useful. We often use we often do in our laboratory and very useful titrations for environmental engineers, as I told you in the beginning. You can also try it very easily in your simple laboratory. Only burette, pipette and only conical flask is required for this type of titration. Only two very common indicators, not rare indicator, very common indicators, phenolphthalein and methyl orange. Now, references for this entire 5 lectures, that is on acids, bases and salts, you can read from Pikadatta and Pikadatta 2000, it is the general and inorganic chemistry, very common textbook, you can easily find it and you can read from that book. And another book, Sword, McCarthy and Parkin, this chemistry for environmental engineering. This is also not costly book, you can easily buy it also for environmental engineering course, and you can read from this book also. Thank you very much.